We are at lecture 32 here today, the week of Thanksgiving, 2016. We only have 2 more weeks after this point, so we have 7 class periods total left. And today, you can see lecture A, I'm going to be giving you what I call a crash course in basic differential equations. And then in lecture B, we'll be doing applications of basic differential equations. We've talked about differential equations to some extent, though not a ton in depth. When we come back from Thanksgiving break next week, we'll get into systems of differential equations where you have more than one differential equation at a time. And we're going to look at phase planes, and we're going to bring in everything that I talked about on sort of a surfacey level with vectors and velocity vectors and acceleration vectors into play. And so it will serve as an introduction to differential equations if you take that in the spring, but also multivariable calculus. A lot of the things that we do in here in the last 2 weeks will involve multivariable calculus as well. So both things will prepare you for that class, those classes if you end up needing to take them. All right, crash course in basic differential equations. Let's review that. Basically, this is stuff that I've mentioned before, but it's always good to see it again. So what is a differential equation? Well, let's come up with some examples and sort of describe what they are as we think about examples. dy dx equals, let's make it x cubed plus sine of 2x. There's an example of the differential equation. Well, why is it a differential equation? First of all, it's an equation. You see an equal sign in there. Why is it a differential equation? Because it's got a derivative. You differentiate, define derivatives, thus the name differential equation. What do you do with the differential equation? You want to solve them, if you can. You want to find a function, not a number, but a function that satisfies the equation. Find a function whose derivative, in this case, is x cubed plus sine of 2x. This is the simplest kind of differential equation. It's what I call a pure antiderivative problem. All you have to do to find the answer is just integrate. Your general solution can be found just by integration. Y equals the integral of x cubed plus sine of 2x. And you want to put the integration constant in there as well. You're going to get 1/4 x to the 4th. Careful, minus 1/2 cosine of 2x plus some arbitrary integration constant. So that family of functions for any C is what we call the general solution. There are infinitely many different possible answers, infinitely many functions that solve the differential equation. They're all of this form. If we add an initial condition into it, so I'll write the differential equation again and put an initial condition here, say y of 0 equals 3. That set of 2 equations is called an initial value problem. And typically, initial value problems have just one answer. Not always. There are some weird cases where you can get more than one answer. But typically, initial value problems have only one answer. To solve the differential equation, the function needs to be of this form. To solve the initial value problem with that initial condition, y of 0 equals 3, we need to pick the value of c that makes that true. So that results in an algebraic equation. We want y to be 3 when x is 0. Careful here, cosine of 0 is not 0, it's 1. So the right-hand side simplifies to negative 1/2 plus c must equal 3. Add 1/2 to both sides, that means 3 is 7. C is 3, 7/2, excuse me. C is 7/2. And your unique solution of the initial value problem is the one function, y equals 1/4 x to the 4th minus 1/2 cos 2x plus 7/2. So the general solution really involves infinitely many functions. that all solve the differential equation with the initial condition, your initial value problem, typically only has one answer. For most of the examples we consider, that will happen. This one function solves both of these things. Gets a little harder when the right-hand side of the differential equation involves y instead of x. Here's the simplest kind where the right-hand side involves y instead of x. dy dx equals y. I hope you remember by now the answer is not 1/2 y squared plus c. You can't just integrate it. You need to think of y as a function of x. In Leibniz notation, we write it like that, and that is the most common way to write things, is with Leibniz notation, or with just a prime like this. With function notation, the equation would be equivalent to this. And that, in a sense, might be less confusing. To emphasize, you're looking for a function, f of x, whose derivative is itself, though this is more traditional. But we are looking for a function whose derivative is always equal to itself. Y is the function of x. E to the x works. Its derivative is itself. Any constant times e to the x works as well. Turns out your general solution in this case is any constant multiple of e to the x. It's not e to the x plus c, it's c times e to the x. Any function like this is a solution. And it also turns out it can be proved that any solution must look like that for some value of c. And c can be anything. There are infinitely many different functions that solve the differential equation. This is really a family of functions that all solve the differential equation. Once again, if I add an initial condition, as will be typical, I get a unique solution. y dx equals y of 0 equals -7. Is going to give me a unique solution. Y equals, you can just think about this, -7 e to the x. That will equal -7 when x is 0. That solves the initial value problem. That's the one function that solves both of these things. It can get harder. And you might have to use that technique, separation of variables. So if I make that a y squared on the right side instead of a y. Now we are looking for a function whose derivative is always itself squared. Y is a function. Again, it really would be less confusing in function notation. We're looking for a function, f of x, satisfying that condition for all x. Its derivative is its square. They're the same. It's hard to guess what the answer might be, so it's nice to have a technique. Separation of variables is the technique. Get all the y's on one side and all the x's on the other, pretending dy dx is a fraction, even though it's not. Divide both sides by y squared. Quote unquote, multiply both sides by dx. You can write the equation like that. You see something like this, you should get an urge to integrate both sides, and so we do. And it is a good thing to do here. This is the same as integrating y to the -2. So the left side becomes -y to the -1. The right side is x plus c. Should the left side involve a c as well? Well, it could. But it's also okay to sort of just think of the c as being on one side by itself. Like that. Now the goal is to solve for y. You can multiply both sides by -1. Maybe I'll call this c1. And then put a plus c there where really c would be -c1. After I multiply both sides by -1. But if c1 is an arbitrary constant, then c can be thought of as an arbitrary constant, and I can use a plus sign. And then take the reciprocal of both sides. Careful, a common mistake here is people, don't write what I'm about to write, people sometimes will think, oh, that means the answer is -1 over x plus 1 over c. No, that's wrong. It's 1 over this whole thing, which which you can write like this, and that cannot be separated into two fractions. That would be an invalid algebra mistake. Invalid algebra step, it would be a mistake. Okay? So this, in essence, is a general solution. It's actually not quite as ideal as possible because all choices of C do not generate all solutions. There's one solution that would be missing, and that is the solution where the function is always 0. If your function is the 0 function, f of x is always 0, its derivative is always 0, and its square is always 0. That function is the solution, but no choice of C here is going to give you the 0 function for an answer. So this is not quite as ideal as it could be, but it's usually okay for most purposes to solve initial value problems as long as your initial condition is not that y of 0 is 0. But what if your initial condition is something else? Consider this initial value problem where I pick something other than 0 here, like 5. Once again, you can figure out the value of C that'll make that work. Take your general solution, plug in y equals 5 when x is 0. That'll mean C is 1/5. 5 will equal 1 over C, so C will be 1/5. So your unique solution to the initial value problem can be written as y equals 1 over 1/5 minus x. It's also okay to multiply the top and the bottom by 5, which doesn't change the function. You can also write this as 5 over 1 minus 5x. Those are the same functions. These are equal. This is the unique solution of this initial value problem. Again, if the initial condition here were 0 instead of something non-zero, technically this is not what you would use. You'd have to recognize that, oh, when your function's always 0, that's also a solution. Because again, its derivative would always be 0 and its square would always be 0. So this is not quite as ideal as possible. Essentially, it's because when we separated variables, we'd be dividing by 0 and y is 0 here. Okay, and that led to us missing the constant function 0 as an answer. Do another example here. We'll talk about this more in lecture B, but the following kind of equation has applications to, for example, population growth. People try to apply this type of equation to population growth.
Why don't you just keep the constant C1? Why do you change it to C?
Oh, just so I could keep a plus sign there.
Okay.
It's not a big deal. And actually, let me change the independent variable to being t this time instead of x. In fact, from now on, I'm going to pretty much use a t most of the time, because a common kind of thing in differential equations is you're modeling how something changes over time. So I'm going to typically use a t now instead of an x. This kind of thing we'll see in lecture B comes up with population models. Can we solve for y as a function of t here? Yes, you can separate variables and integrate. The right side is easy to integrate, t plus c, I think I'll call it c1. Eventually I'll call the constant c, but I'm just going to modify my constants. Left-hand side's harder to integrate, but we can. We can use partial fractions there. We're integrating 1 over y times 5 minus y. Can we write that as some constant a over y plus another constant b over 5 minus y? Can we solve for a and b that make that work no matter what y is? The answer is yes, you can. And you can use the trick that we saw to find a and b. You can multiply both sides by the common denominator here, y times 5 minus y, to get rid of the fractions. You get complete cancellation on the left, leaving you with just a 1. On the right, you get partial cancellation. Multiply this by y times 5 minus y, and the y's cancel. leaving you with a times 5 minus y. Multiply this times y and 5 minus y, and the 5 minus y's will cancel, leaving you with just b times y. Quickest way to solve for a and b are to plug in values of y that simplify this expression a lot. For example, if y is 0, that goes away. This becomes 5, and a is 1/5. Plug in y equals 5, and that one goes away. This becomes a 5b. So b is also 1/5. Doesn't always happen that those are equal. Sometimes it does. Technically, I haven't proven that these a's and b's work. Just derived the possibilities, essentially, but they do work. And so we would integrate then 1/5 over y plus 1/5 over 5 minus y. Can I do that right away without writing an integral sign? Integrate 1/5 over y, you get 1/5 natural log of what the absolute value of y. You should keep the absolute values in here because theoretically y could be negative. And careful, because of the minus sign here, you're going to get a minus sign there when you integrate it. If you did a substitution, you'd let w equal 5 minus y. dw would be negative dy. Put absolute value signs in again. Use properties of logarithms to combine these into one logarithm. This is the same as natural log of, well, you can put absolute value signs around the whole thing if you like. Y over 5 minus y, or 5 minus y up to the 1/5 power. You can exponentiate now to get rid of the logarithm. And it does turn out you can get rid of the absolute value signs. I'm not going to justify that completely here. I'm just telling you you can get rid of them in your quest for a general solution here. So I exponentiated and got rid of the absolute value signs. Technically, because of properties of exponents, I can write this expression like that. Maybe I should keep the absolute value signs there initially because this would be a positive quantity. But I can get rid of the absolute value signs in my quest again for the general solution and let C be really plus or minus C2. So C2 here is e to the C1, and C itself is essentially plus or minus C2. The absolute value of C would be C2. Just, having these intermediate constants till I get my final constant, which I'm just going to call C. It's not a real big deal if you just call it C the whole way. C1, C2, and C are arbitrary constants. Doesn't really matter what you call them. I'm being a little sloppy here, but this is fine. Question?
So by getting rid of the absolute, or by having them there, you can change the minus to a plus.
Well, by having them here, essentially I'm sort of thinking of C2 as being positive, which e to the C1 would have to be positive. C2 would have to be an arbitrary positive constant, but effectively by getting rid of the absolute value signs, I allow C to be a negative constant in this expression.
But that's why you have 5 plus y at the bottom?
This is a minus. Okay, this is not rigorous math, okay? I'm just sort of waving my hands and saying this is going to be good enough to help us find the answer. Might have been good actually to have the 5 on the other side to begin with as well. I could have done it that way, then I wouldn't have had to worry about a 1/5 power. but it's done, it's okay. Maybe I'll call this C3 actually, because now I'm gonna raise both sides to the 5th power to help me solve for y. I think I'll call this C now. This C is C3 to the 5th power. Okay, again, it's not a real big deal to have these different C's. Some people are sloppy and have the C the whole way and don't give her different names. It's not a big deal. Okay. It is confusing, I know, but it's not a big deal what you call it. We can be sloppy there. We want to solve for y. Go ahead and cross multiply. That will help you solve for y. That's what you get when you cross multiply. Now get the y's on one side by themselves. And factor out the common factor of y. What I did here was I added cy e to the 5t to both sides. And then I factored on the left side. You see what I did there? I added this to both sides. So it canceled on the right, and I got a plus cy e to the 5t on the left. Then I factored out the common factor of y, so I did 2 algebra steps there in one. We're almost done. You want to solve for y? Divide both sides by this. Y is then 5c e to the 5t over 1 plus c e to the 5t, where c can be anything.
So, I'm a little bit confused. When you have y equals 5c e to the 5t minus, I'm confused, yes, how you got from there to the 1 beneath it.
Yeah, that was what I just said a minute ago. I added this to both sides
Okay.
to cancel on the right. And on the left, then I get a cy e to the 5t.
Mm-hmm.
I have a y there already. I can factor the y out of those 2 terms to make this. So I did 2 algebra steps at once there.
Okay, so you just added the cy e to the 5t.
Yep, both sides first.
Okay, and then factored that. Okay.
Yep. When the algebra seems to go too fast for you, that's a signal that you should check it quick after class. You should look at your notes as soon as you can after class and try to check something. It's always a good idea. Some people have a hard time following the algebra when it goes fast. Many people do. Okay? So if you do, if that's you, you should check it quick after class. That was a complicated enough calculation that I want to check to see if it's right. Let's use Mathematica to help us check it. One way to check it is to just define a function. I could call it y of t, I can call it f of t, it doesn't matter. That equals what we see here. 5c, I think I'll use a lowercase c because I think maybe an uppercase c is reserved, times e to the 5t. Got to use a capital E, remember E, divided by 1 plus c times e to the 5t. Is this function a solution of the differential equation? I hope so, it should be. What would make it be? It would be, is its derivative always equal to itself times 5 minus itself? I'm saying itself for the y, because y is the function. What's its derivative? Kind of complicated. Let's see how it simplifies. And what is itself times 5 minus itself? Maybe you'll have to simplify here as well. They're the same. How about that? That means it solves the differential equation. Okay? And you could check that by hand. Differentiate this with the quotient rule. Simplify. You could also go 5 minus this, you'd have to get a common denominator with the fractions, and then multiply, once you simplify 5 minus this, multiply that by this, and simplify again. In both cases, you get the same thing. That's pretty amazing, I think, that worked, okay? It's worth checking. There's another way to try to check it in Mathematica, and that's to use something called DSolve or DSolveValue, which are built-in Mathematica functions to try to solve differential equations. However, I'll warn you that they don't necessarily produce the answer in the same form that you may have gotten it by hand, so it might look different, but it should be equivalent. Anytime you're solving equations in Mathematica, you need double equal signs. And even though in the differential equation I don't put the t's on the right side, I do have to do that in Mathematica. In the differential equation itself, back up here, there's no t's on the right side. You have to remember when you look at that kind of equation that y is a function of t. You're trying to find y as a function of t. It's not traditional to explicitly write it in. But as far as Mathematica is concerned, you do need to explicitly put t in there to emphasize y as a function of t to Mathematica. We're solving for y of t, so we put a comma y of t, and then we emphasize that t is the variable that we are solving with respect to. It's the independent variable. You know, if you had some other letter in there, some constant, perhaps you might, like a c or a d or whatever. If you don't put that extra comma t at the end, you're not really emphasizing enough that t is the independent variable. So this is going to give us some sort of answer. It may not look the same, though. It looks a little different. Different than what? Different than this is what I'm talking about. Though somewhat similar. Are they equivalent? Well, not perfectly equivalent, because essentially the integration constant is this thing, which can only be positive. So this thing as an arbitrary constant doesn't match our c as an arbitrary constant. For one thing, because it's positive. For another thing, it doesn't look quite the same. I mean, I don't see a 1 on the bottom, for one thing. Could I do some algebraic manipulations to make these equivalent? Let's see. If I sort of think of this e to the c1 as a c, maybe I should call it d, just, well, these. Okay, I'll call it capital D just for something different. So Mathematica is sort of writing the answer like that. If I divide the top and the bottom by d, what would I get? If I divide the top and the bottom by d, here's what I get. And this thing is basically equivalent to this, with c equal to 1 over d is the relationship between these two things. So it is basically equivalent. Except, again, that e to a power would not be negative. This is not a negative arbitrary constant, whereas we want to allow our arbitrary constant to be negative. I can now also add an initial condition and solve the initial value problem. This is infinitely many functions that solve the differential equation. What if I had an initial condition? Say y of 0 equals 4. Can I solve for c in my answer to make that happen? Yeah, I think I should be able to. Plug in y equals 4, replace t with 0. I get 5c over 1 plus c because e to the 0 is 1. Solve this equation for c by multiplying both sides first by 1 plus c. And then subtract 4c from both sides, and you'll get c must be 4. If you subtract 4c from both sides, it'll simplify to that. C must be 4. So the one solution of the initial value problem, if I plug in c equals 4 there, can be written as y equals 20 e to the 5t over 1 plus 4 e to the 5t. That one function should solve the initial value problem where it's the differential equation plus this initial condition that y of 0 equals 4. Let's see what Mathematica produces for that. I wanted to add the initial condition in there. I do that in a list that includes the differential equation and the initial condition. There we have, instead of just the differential equation, in the first argument of DSolve, I'm now putting a list. See the curly braces? The first element of the list is the differential equation, comma, the second element of the list is the initial value that you want to be true. Will this produce the same thing that I had in red over there? Was that something you could see with the camera? Okay, you zoomed in. Well, it gives me a little warning, but it does produce an answer, and look at that answer. That is the same as the answer on the board over there. Those are the same. So it did solve the initial value problem and confirm what I got. DSolve produces the answer in kind of a strange form. Double curly braces, y of t arrow, that's kind of weird. It's called a rule, it's got its uses. There's another command called DSolveValue that's newer, that sort of just leaves the answer in a simpler form. I put the word value in here. Now it just gives me the formula for the function without all the extra stuff. So that's a bit nicer. Okay? So these are some basic fundamental differential equations. There are plenty of others. There's infinitely many different differential equations you can write down. Before break, I want to show you one more kind. In our crash course in basic differential equations. Something called a second order equation. And we'll keep it simple. I think I'll go back to x as the variable, but I could keep it at t. Well, maybe I should go back to t. Let's keep it as t, excuse me. The second derivative of some unknown function instead of the first derivative equals some expression involving the function. And the most common kind of example to consider here is negative y. Find a function whose second derivative is the opposite of the function. Y is still the function. In function notation, this would be saying f double prime of t should equal negative f of t for all t. Can you think of a function whose second derivative is its opposite? I bet you can. Cosine of t, sine of t, those both solve the differential equation. And in fact, the general solution, it turns out, is some arbitrary constant, a times cosine of t, plus another arbitrary constant, b times sine of t, where a and b can be any numbers. Any function like this does solve this differential equation. Its second derivative is its opposite. And it also turns out any solution of this differential equation can be written in this form. Both of those facts are important. You need two initial conditions. And I think I'll think of simple initial conditions here. Let's say y of 0 is 1 and y prime of 0 is 0. The unique solution of this second order differential equation, second order because it involves a second derivative, with these two initial conditions. You need two initial conditions for second order equations. I hope you see just by thinking about it should be cosine of t. A would be 1 and B would be 0 to solve these initial conditions as well. That function has an initial value of 1 when t is 0. Its derivative, negative sine of t, is 0 when t is 0. That one function solves the differential equation along with the initial conditions, that initial value problem. All right, let's take our break.